In 4.5, we're looking at isosceles triangles and equilateral triangles and use some of those properties in proofs. But first we need to know what an isosceles triangle and some of the vocabulary that goes with it. So first of all, when we're talking about an isosceles triangle, our definition of an isosceles triangle is simply that we have one pair of sides, at least one pair of sides congruent. So this would be the only markings we need if they give us definition of an isosceles triangle, where they tell us isosceles. This is our definition. We know the sides are congruent, or the other way around. If we know the sides are congruent, we know it's isosceles. Some of the other vocabulary that will go with this then is the base, which will be the side that is not one of the congruent sides. The congruent sides are called legs. Then we also have the base angles going with the base and the vertex angle between the legs. Our first theorem dealing with isosceles triangles is looking at if we know that the sides are congruent, then that tells us something about the base angles that are opposite of that. So our proof for this would look like this. Now the book starts by giving you a little more information than is necessary. We're going to just start with our only given information that this is an isosceles triangle, or really xy congruent to xz. So that's my given. But what I'm going to start with is constructing an angle bisector. And what this means, and we haven't learned this construction yet, but it means that I can construct, there's only one way that I can draw the bisector coming through here. So I'm splitting this angle up at x, up at the vertex, so that this angle 1 and angle 2 will be the same. So an angle bisector is cutting it in half. When I do that, I will know, first of all, that angle 1 and 2 are the same, because that's my definition of an angle bisector. I will also notice that x to b here, which I've already marked, is congruent to itself, so it's a reflexive property. Now using that, I can show that each side of this isosceles triangle is a congruent triangle. They're congruent to each other, looking at yxb, congruent to triangle zxb. And looking at the matching parts, we were originally trying to show that y is congruent to z, our base angles here. Notice in our name of these congruent sides, we see that those corresponding parts match, and so we know that the base angles then of any isosceles triangle will be congruent. Now we can also use the converse of this. We can switch it around. This time we know that if the base angles are congruent, then that's going to tell us something about the sides opposite. The sides opposite them will be congruent. Now to do the proof of this one, it would be very similar to what we did on this one, except that we would start the same way, where we would make an angle bisector. Remember what was given to us though. We had the base angles are congruent, so I would mark these differently. 1 and 2 are congruent because we made the angle bisector. We would still have the reflexive property. The only difference in this proof would be that we are looking at angle side to prove that the two triangles are congruent. And then we could use corresponding parts to show that the sides CA and CB are also congruent. Our next theorem is looking at what happens if we do look at the angle bisector. So another consequence of dealing with this angle bisector here is something that happens to this angle down here, actually the whole side. First of all, it's going to be perpendicular, and that'll be the midpoint there. Now we can actually see why that works if we come back to this proof here. If we saw that these were congruent triangles, then we know that these two angles would also have to be the same. Since it's a linear pair, they would have to be each a right angle. We would also see from the corresponding parts that this part of it would have to be congruent to that part. So we end up with a perpendicular bisector every time we have an isosceles triangle. And maybe I should put with my if part, we also need to know that this is an isosceles triangle, because if we don't know that, the angle bisector does not always guarantee that I have a perpendicular on the other side. That only works when these two sides are the same. Now we could use this in a problem like this one here. My base angle here is 54, and I'm asked to find x. Now since this is an angle bisector, and I have congruent sides, so isosceles triangle, angle bisector, that means I have a 90-degree angle here. If that's a 90-degree angle, and then this would also be a 90-degree angle, but also this angle bisector tells me this angle would be x. So I have here 54 plus 90 plus x will be equal to 180. And if I simplify that and move everything to the other side, that's going to give me x is equal to 46. Next thing we look at is called a corollary. A corollary is a theorem that we can prove by using, so we just did that proof with the isosceles triangle, and actually equilateral triangles we can think of as a pair of isosceles triangle. We can think of it as an isosceles triangle either in having these two as my congruent sides, but also these two would be congruent sides, so they all end up being congruent. So if I look at these two, that would tell me that these base angles are congruent. And then looking at this one here would tell me these base angles are congruent. So if I link with using the transitive property, we see that the top, these two are the same. We do some substitution here. We find since all of these angles are the same, then basically we have 3 times whatever that is to get 180. So each one of those angles has to be 60 degrees in every isosceles triangle. So what this theorem is saying basically is if we know that all 3 sides are the same, then we also know that all of the angles are the same. That would be corollary to theorem 4.3. So basically we could really just say that if it's equilateral, it's equiangular. We could also turn it around. This is a biconditional statement. We can prove it the other way around, that if all the angles are the same, then all of the sides are the same.